This is part 4 of the series Integration, and in this section we're going to be looking at some very important mechanical tools that will allow us to handle the area problem in integral calculus. And this idea is called sigma notation. Now, sigma is the Greek letter that stands for summation, and what we're dealing with is the sum of some number of terms that are written in sequence. So the sum, sigma, as I equals 1 to n of some expression a sub I, this I is the counting index or the index of summation. This is the thing that's going to change from its low bound, which is what this 1 is, this is the lower bound of summation, to its upper bound, n. In this case, there is no upper bound, it's just n is some number n terms. We could have specific summations. For example, if we had the sum as I equals 1 to 6 of the counting index I, what you would basically be doing is setting I equal to 1, then incrementing I and adding it to the next one, and then incrementing it again and again and again and one final time until I is set to 6. And that's the general idea behind summation. Now, obviously this would be very, very tedious to handle if we had multiple terms and multiple expressions that we were summing across. So we have several rules or formulas that allow us to perform these summations a little bit easier. Now here we have several formulas that we're going to be using, and let's just take them one at a time. In this first formula, we have some constant times the ith term of our summation. Now, because this constant has no counting index, it really doesn't enter into the summation process. So we can pull that constant out and you multiply it by whatever the result of that sum is. In the next one, this is similar to the addition and subtraction properties that we looked at for integration and differentiation. If you have the sum of two terms that have a counting index in them, we can separate these as two separate sums. So it would be the sum of the first term with a counting index plus or minus the sum of the second term. And this would go on for however many terms you may have. You can chain these together. The next one is a little bit more straightforward. This is just saying that if we have the sum of some constant, let's say it's the sum of 5, from I equals 1 to 5, you would just be adding 5 to itself n times. So we would just multiply that constant times that upper limit of summation. Pretty straightforward idea there. These three, not so much straightforward. I'm not going to go through the derivation of these formulas, but if we have the sum of some counting index from I equals 1 to n, that's equivalent to taking that upper limit times the upper limit plus 1 divided by 2. When we have the counting index squared, it's n times n plus 1 times 2n plus 1 over 6, and the counting index cubed, n squared times n plus 1 squared over 4. Now, there's several techniques that you can come up with to memorize these things. It's really not important which one you use and how you do it. Some people like to expand these out so that they have some quadratic. It's easier for them to remember. However you choose to do it is your choice, but these three forms are going to be crucial to the remainder of our discussions in the first part of this area problem situation. So let's go ahead and try an example to see if we can get a better handle on some of these formulas. In this problem, we need to evaluate this sum for n equals 10, 100, and 10,000. Now, we're not going to obviously go through and insert every term for 10 times, 100 times, and 10,000 times. We're going to use our formulas to develop expressions that allow us to just plug in numbers and solve for these sums. So to start out with, we can see that we have a term in the denominator here that's an n term. That n is a constant, and we can employ that constant rule that we saw just a little while ago so that we can pull out that constant term and just deal with our changing terms. So let's begin by rewriting this as 1 over n squared times the sum for I equals 1 to n of I, and I'm going to separate this into two separate sums. You don't need to do this. I'm going to do this just for the sake of clarity. So plus the sum for I equals 1 to n of 1. And this whole thing is being multiplied by 1 over n squared. Now, this summation is one of our sum formulas, so let's go ahead and write that. That is n times n plus 1 over 2 plus this is just n times the constant. So there's two of our formulas that we had to deal with. Let's go ahead and simplify this. We're going to treat this as a variable, even though eventually we're going to substitute in a number for that variable. But we're going to treat this as a variable expression. So we have 1 over n squared times n squared plus n over 2 plus n. Now we can combine these into one term. So we have 1 over n squared times this is n squared plus n. This times this, using that sign, is plus 2n over this times this, which is just 2. Give ourselves a little space here and combine our terms. And so we have 1 over n squared times n squared plus 3n over 2. And we'll go ahead and multiply these together. And that gives us n squared plus 3n over 2n squared. Now, we can see that we have a common n term all throughout here. So we're going to divide all these things by a common n. So we have n plus 3 over 2n. So this is our final expression, and we're going to evaluate this at n equals 10. So we have 10 plus 3 over 2 times 10, which is going to be 0.65. And we'll have 100 plus 3 over 2 times 100, which is 0.515. And then we have 10,000 plus 3 over 2 times 10,000, which is 0.50015. So just a quick example of how to evaluate sums. And we're going to be doing quite a bit of this, so we're going to get a lot of practice. So let's move on to the next section. In this section, we have reached the essence of the area problem of integral calculus. And we're going to be investigating this in excruciating detail. And so let's go ahead and jump into these rather formidable looking pictures, which are rather simple when we analyze them, but they may look a little confusing and a little intimidating at first. So here what we have is the graph of a function. This is the function that each of these are the graph for. And our goal in the area problem is to find the area enclosed by the graph of a function. That's fundamentally it, to find out how much area is enclosed underneath these graphs. Now, to start this idea, you can see that we can approximate the area by finding the area of multiple rectangles that are inscribed in this graph of this function. And by inscribed, I mean the rectangle is completely enclosed underneath the function itself. This type of summation, where we sum the areas of rectangles, is what's known as a lower sum, because in this case the function is decreasing here and we're using right endpoints. You can see that there's pieces missing of the area. So this summation of these areas of these rectangles is always going to be a little bit lower than the actual area under the curve. In contrast, if we look at, for the same function, we look at the left endpoint defining the height of these rectangles, we can see that we're going to have a little bit more included in the area of those rectangles than is actually encompassed underneath the graph. These we're calling circumscribed rectangles, and this is known as an upper sum. So a lower sum is always going to be a little bit less than the area under the curve, and an upper sum is going to be a little bit more than the area under the curve. But the idea here is basically the same. We want to find the area of each one of these rectangles and add them together. Now, to find the area of each one of the rectangles, we take the width times its height. Now, the width, we're going to make a simplifying assumption that the width of each one of these rectangles is the same, or we say these rectangles are of uniform width. And we can find the width of any one of those rectangles simply by taking the upper bound of our summation minus the lower bound divided by the number of rectangles we're summing across. So that's the width. The height is going to be dependent on evaluating the function at some x-coordinate within each one of these sub-intervals. So this at these x sub I points. Now for this lower sum, we're going to be using the right endpoint. And with the right endpoint, we evaluate f at that right endpoint. So we would say that this is the ith subinterval. This is the ith I plus 1, I plus 2, I plus 3, and so on. Over here for an upper sum, we're using the left endpoints. So if this is the ith endpoint, this is the I minus 1 endpoint. So that's going to come into importance when we deal with the actual summation formula. So to find the sum, the area under this curve is going to be given by the sum for I equals 1 to n, the number of rectangles that we're finding is the n, times the area of each rectangle, that is the height, f of x sub I, times its width, delta x sub I. Now over here for the left endpoints, since we're not dealing with this endpoint, we're dealing with this one, and we want the ith subinterval, we always have to subtract 1 from the I so that we use this left endpoint instead of the right endpoint here. So the formula is almost the same, except it's going to be x sub I minus 1 instead of x sub I. But the idea is identical. We're finding the width of each one of these rectangles, multiplying it by its height as we increment out from left to right. So let's go ahead and put this into practice and see if we can't solidify some of these ideas. We're going to be doing this quite a bit, so hopefully you'll get some good practice.